Okay, welcome back everyone. First off, can someone tell me if they can hear me? Okay, good. Thank you. So as usual, we have about 5 minutes before the official class start time. Does anybody have questions for me? It's very blue. Yeah, the white balance seems to be a bit off. I can't really adjust it much. It's supposed to be doing that automatically, but for whatever reason it's not doing a great job. The other video will be better, hopefully. Have we covered all the stuff in assignment 1? We have not covered every single thing you need for assignment 1. In particular, we will be doing binomial coefficients at some point, and those are needed for one part of the assignment. So the binomial coefficients, I'll tell you now. They're what you get when you ask how many ways are there to choose some number of things, k things, from a larger set of size n. So a lot of assignment 1 you can get working on now, but like I said, you're still missing binomial coefficients. Have office hours been fixed? Not yet. I think my current plan, because the people who support us on CU Learn have been a bit slow to do the merge that I want, is I'm going to suggest that we change our office hours to use Google Meet. I did that yesterday with my office hours. It was simple and it seemed to work well. It supports screen sharing and chatting. That's probably all we need for office hours. Any other questions? Okay, then we'll just wait in awkward silence for a minute and a half. By what lecture will we be ready to answer all the questions on assignment 1? I forget the lecture schedule, but by the time we do binomial coefficients, I think you should be able to do just about everything. And even if you're anxious, then you come across a question where somehow you need to answer how many different ways are there to choose k things from some set of size n, and then you can just go ahead and look ahead and see what's there, because the definition of these binomial coefficients is not difficult, and you can skip ahead to that. Aren't there lectures from previous years that contain binomial counting? Yes, all the lectures from previous years are up there. Scroll down the list of topics and you'll see binomial coefficients is in there. A lot of the stuff is looking pretty confusing so far. That's understandable, so what I suggest is you start working on it, do as much as you can, and when you get stuck on something, see the TAs. And the sooner you start that, the better off you'll be. Yeah, so next Monday you'll learn binomial coefficients. Okay, so we're good to start now. So we're still on the topic of combinatorics, counting, figuring out the sizes of sets, and that means that we're going to look today at a few different rules that you can use to figure out the sizes of sets, and a really common one and surprisingly powerful one, even though it's trivial, is what's called the bijection rule. So we've used it already, we'll see that in a second, but first I need to tell you what a bijection is. So a function from a set A onto a set B is a bijection if it's one-to-one and onto. And in more classic math language, one-to-one is sometimes called injective, so an injective function, and onto is sometimes called surjective, a surjective function. What do these things mean? One-to-one says that if I take anything in B, some element y in B, there is at most one thing in A that maps onto y. So here's a picture of a bijection, and indeed, if I take any element y, for instance this one, I look in A, how many things in A map onto that? Well, there's at most one. Okay. And onto says that if I look at anything in B, for instance, again, we look at y, there is at least one thing in A that maps onto y. So of course together, if you're one-to-one and onto, that means if I look at anything in B, so any element y in B, there's at least one and there's at most one things in A that map onto B, so that means there's exactly one thing in A that maps onto B. So that's an injective function. What you're not allowed to have, so what are the things that prevent you from, that's a bijection. What are the things that prevent you from being a bijection? Well, you can violate one-to-one, which is when you have two or more things in A that map onto a single element of B. So in this case, it's not one-to-one. Or you have in B some lonely element that nothing maps onto. Okay. So this one here is not onto, and that's because there's this element down here and there's nothing in A that maps onto it. Okay? So these are examples of things that prevent you from being a bijection. And now the bijection rule is trivial. It says if there exists a bijection from a set A onto a set B, then the sets A and B have the same size. That's trivial, right? And that's just because a bijection is really a matching. You're writing down a bunch of pairs. Each element in B appears in the second part of the pair and the second half of exactly one pair. Each element in A appears in the first part of exactly one pair. So the number of pairs is exactly the size of A, but the number of pairs is also exactly the size of B. Okay. Is that clear? Any question about that? So this is a classic bijection. This drawing shows is, it's a matching between A and B. Okay, good. And I told you that we've already used the bijection rule, and we used it already last class, because in last class we studied the product rule, which is probably the most powerful rule that we have for figuring out the sizes of various sets. And when we did that, we implicitly defined two sets A. So we defined some procedure P that generated, so we're trying to figure out the size of the set S. We defined a procedure P that generates elements of S, and we counted the number of executions of the procedure P, the number of different ways P can execute. That was easy to count. It was just the product of the number of choices we have at each step in the procedure P. So that was easy. So A was the set of possible executions of the procedure P, and B was the set S that we're trying to compute the size of. And remember, we had these two conditions. The conditions were that if the procedure executes in two different ways, then that should generate two different elements of S. That's the one-to-one thing. So there should not be two different executions of the procedure that generate the same element in S. And the other condition that we had was that it should be the procedure for every element in S, it should be possible to execute the procedure so that you get that element of S. In particular, there shouldn't be anything that you're trying to count, but there's no way that the procedure could generate it. So that would be this picture here. So that's the onto condition. So those two conditions were basically establishing a bijection between the set of possible executions of the procedure and the set S, whose size we were trying to figure out. Okay. All right. So let's look at another example. Let X be an n-element set. So for example, maybe X is equal to A, B, C. So there's a 3-element set. And P of X is the set of all subsets of X. So what's that in this example? In this example, P of X is supposed to be a set of subsets of X. So what are the subsets of X? Well, there's the empty set. So the empty set we write kind of like a 0, but with a longer line through it. So that means that there's nothing there. Then there are the 1-element subsets of X. Or let's try it. Let's write them. I'll write them out in an order that will help it maybe make sense shortly. So let's say there's C. There's B, there's BC, there is A, there's AC, there's AB, and finally there's A, B, C. Okay. So this thing here, which was called the power set of X, has, let's count them, 1, 2, 3, 4, 5, 6, 7, 8 elements in it. So each element of the power set is one of the possible subsets of this set X. In this case, 3 things in X, we get 8 things in the power set. Okay, is it clear? This definition of the power set clear? So somebody please enter something, anything, just so that I understand whether you guys are still there or not. Okay, good. Thank you. All right, so there's the example. And so we would like to know, this is an example with n equals 3. And in that case, the size of the power set of X is 8. We'd like to know what happens in general. And we'll do that with the bijection rule. And here's the way to do it. We'll say let X, just give names to its elements. Give them some order. X1, X2, X3, all the way up to Xn. And then for any subset, let's say S, a subset of X, let's define a function. Define f of S to be a binary string, B1, B2, B3, up to Bn. And it's defined this way, where Bi is either 0 or 1, and it's 0 if xi is not in the subset, and it's 1 if xi is in the subset. So again, let's look at this example. Let's call A x1, B x2, and C x3. So those are the names we've given to the elements in our set in some specific order. And we can look at a couple of examples of what this function is. For instance, f of the empty set. So it's supposed to be a bit string of length 1, 2, 3. And the bits tell us whether or not the particular element is in the set. 0 if the element is not in the set, 1 if it is in the set. So the first bit tells us whether A is in the set, and A is not in the set because it's the empty set. The second bit tells us whether B is in the set. In this case, B is not in the set because it's the empty set. And the third bit tells us whether C is in the set. In this case, it's not. So that's kind of a trivial example. Let's do a different set. If I look at f of AC, so that's this one here. A is in the set, so the first bit is 1. B is not in the set, so the second bit is 0. And C is in the set, so the third bit is 1. Okay. So, is that clear, what this function f does? It's basically just a bit vector that tells us whether or not each element is in the particular subset that is the function's argument. Okay, so we could write this down. we could write down the value of f for all of these things. We would get 8. We get 8 values because there's 8 things in this power set. Anybody want to tell me what those 8 values are in words? Zero, zero, zero will be one of them. This one here is going to become 0, 0, 1. This one here will be 0, 1, 0. This will be 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's all the binary strings of length 3. Okay. So, what does that mean? Well, at least in this example, and you can check that in general this is true, F is a bijection from, what are the arguments of X, of F? They are subsets of X, and so everything in the power set, this what's called the power set, P of X, is a possible argument for X, so that's the A. And what does it map onto? Well, it maps onto binary strings of length n. Okay. So, there's a bijection from P of X onto binary strings of length n. So that means that the size of P of X by the bijection rule is equal to the size of Sn. This is something we studied last class. Sn is the set of binary strings of length n. And the size of Sn, we saw last class, it was the easiest possible application of the product rule, because for each bit in the binary string you have 2 choices for that bit. It's 2 to the n. So by the bijection rule, the number of subsets of an n-element set is exactly the same as the number of binary strings of length n, which we figured out already is 2 to the n. That was the application of the product rule. Okay. And if you wanted to prove this with the product rule, just using the product rule directly, of course you could, because there you would need a procedure that generates these things, and the procedure would just be walk through x1, x2, x3, and so on, and for each one you need to decide whether to include it in the set or not to include it in the set. That's 2 choices. You have to make those choices n times, so you get 2 to the n. So the procedure is almost exactly the same as writing down a binary string, but instead of writing 0 or 1, you're writing put this element in the set or don't put this element in the set. Okay. All right. Would anyone like to pause here? Can we construct a formal proof? I think the only thing that was not formal about this is that I said f is a bijection from the set of these things, the set of subsets of x, onto binary strings of length n. And what's missing to really finish that and be extremely rigorous about it, we would have to say, okay, first prove that it's one. So it's certainly a function from these elements onto binary strings of length n. That's clear. Is it one-to-one? Well, if I take two different subsets of x, then why are those two subsets different? Well, they're different because one of them has xi in it and the other one doesn't. Well, that means that the binary strings that those two things generate will be different at position I. And so that tells us that we never have two things of x, two subsets of x, different subsets that map onto the same binary string. So that establishes that it's one-to-one. And to establish that it's onto, so that means that we need to make sure that every possible binary string of length n, for every one of those, there is a subset that generates it. But indeed, that's, again, easy to check. Give me any binary string you like. I'll just write it down right beside this thing here. So 0, 0, 1. Is there a subset that generates that binary string? Yes. It's the subset that does not include A, does not include B, and includes C. And for anything you write down here, the bits of the binary string just tell me what to put in the set that will generate that thing. So that's as formal as one needs to get. If by formal you mean, is there a sequence of sort of mechanical things that we can do in the sort of way when you do integrals or derivatives in calculus, where at each step you're applying some rule? Not really, unless you want to get into a formal logic system for dealing with sets. Those exist, but proofs are incredibly long in those systems. So we have to argue using, sound logic and the normal rules of reasoning. Okay, good. So that's the bijection rule, a fairly simple one, but often powerful. Here's another nice rule, easy one, called the complement rule. So the way to think of the complement rule is in terms of a universe and a set that we're trying to study. So we have some big universe, which again, a universe is just a set. And inside of that thing, so A is a subset of this universe, we have this set that we would like to know the size of. Okay? So we write that as if A is a subset of U, then the size of A, what you do is you take the size of U and you subtract the size of U minus A. All right, that looks complicated, but let's see what this really means. So U is this big box, contains everything, including A. A is in here, and then outside of here, so in U but outside of A, is this thing, U minus A. And so if I want to know how big A is, it's enough for me to know how big U is and how much of U is not contained in A. Right? Start with U, take away everything that's in U but not in A, and what you're left with is A. So start with U, take away the number of things that are in U but not in A. What you're left with is the size of A. easy easy rule. Looks like it's somehow complicating things more than necessary, but actually sometimes it's really helpful. Very often it's much easier to compute the size of the complement than it is to compute the size of the usual thing, the main thing. So this is called the complement rule. And let's look at an example. Here's one from computer security. Let's say that a password, we'll define it this way, is a string of 8 characters over the alphabet It's an alphabet that contains all the lowercase characters, A, B, C, and so on, up to Z, but it also contains the digits 0, 1, 2, and so on, up to 9. So that's the alphabet, and to make it hard, we'll say that contains at least one digit. Okay, and what's a digit? These are the digits. These other things are letters. So you've probably encountered some kind of annoying password system like this that forces you to pick a password that's not too short and not too long. In the extreme case, it needs you to pick a password of a very exactly some length. And the annoying part is, well, it can't just be something that uses only letters. You have to include at least one special thing. In this case, it's a special digit. So then the question is, well, how many possible passwords are there? So let S be the set of possible passwords. And I would like to know what the size of S is. Certainly, knowing the size of S is important for security purposes because it tells us the complexity of a brute force attack where someone, if they have the time, just tries every possible password. All right. It turns out that this is tricky to study directly, and the reason is this constraint that says the password must contain at least one digit. And the problem is the at least, although there's even if it was exactly one digit, there would still be some issues. Because if we try and count directly, then basically we have to count the number of passwords that contain one digit, and the number of passwords that contain 2 digits, and the number of passwords that contain 3 digits, and so on, all the way up to 8 digits. So instead we'll go the other way and use the complement rule. So we'll say let U equal the set of all 8 character strings over sigma. Okay. So I'll let you write the universe U is going to be anything 8 characters long that you can write using these characters. Okay. So what do we know? We know that the size of sigma has 26 letters plus 10 digits. So the size of sigma is 36. And the hope is then, well, hopefully the size of U is easy to compute because we're going to try and use the complement rule here. So 8 character strings over an alphabet of size 36. Anybody want to tell me how many of those there are? What does over mean? Over in this case just means they're strings that you can write, and each character in the string is taken from this set. Yep. All right. So everyone is telling me that the size of u is equal to 36 to the power 8. And why is that? The proof of that is you use the product rule with an 8-step procedure. And you have 36 choices or options for each step. Okay. So if I want to write a procedure to make one of these 8-character strings, well, the procedure is write down the first character, write down the second character, write down the third character, and so on, up to the 8th character. The number of ways to write down the first character is 36, and the number of ways to write down each other character is also 36. So we get 36 times 36 times 36 times 36, 8 times, 36 to the power 8. This is exactly the way we counted binary strings, but with binary strings the size of sigma was just 2. Now it's 36. Okay, good. So the size of u is easy to compute. What about u minus a, or u minus, I guess we're calling it s. So these are the set of passwords. So in language, plain language, what is u minus s? So these are all the 8-character strings that don't satisfy the requirements of the password. Well, the only requirement is that those things should contain, a password should contain at least 1 digit. But if you don't contain at least 1 digit, then you contain 0 digits. Okay? So these are strings over u with no digits. But if a string is over this alphabet and it has no digits, but that means these are just strings over this alphabet that has only the letters in it. Right? If I write down an 8-character string and it's not a good password, it's because it has no digits. It means it has only letters. Okay. So how many 8-character strings are there that I can write down that use only letters? (26 to the 8), exactly. Okay. So now we're golden. We have everything we need to use the complement rule. We know the size of u. We know the size of u minus s. That means we know the size of s. So therefore, the size of s is equal to the size of u minus the size of u minus s is 36 to the 8 minus 26 to the 8. And I can tell you exactly what that is. It's big, but not enormous. So what are we looking at here? There's 2.6. So there we're up into the billions. Yeah, so like 2.6 trillion or so. So it's big by, you're not going to brute force this if you have to type in these passwords. Try each password by hand. But if a computer is doing it, this is, you know, a feasible thing for a computer to do in a small amount of time. And that's why these password systems don't let you just try, don't let you try logins or sign-ins, you know, as fast as the computer can handle it, because then these kinds of attacks would be reasonable. Okay. So this is the number of valid passwords in this particular password system. Question about that? Okay. That's the complement rule. Let's look at another rule. And these rules are, again, like the product rule, the bijection rule, now the complement rule. They're somehow really easy rules. There's nothing difficult about them. What becomes difficult, or what becomes clever, is that there are sometimes really non-obvious ways to apply these simple rules to solve problems that look impossible otherwise. So already, the complement rule is kind of trivial, but already if you didn't see it, you wouldn't really know how to do this password question without it. That was already sort of a non-trivial thing. Moving to the complement really made life a lot easier, because if you had to start counting the number of passwords that contain exactly one digit, and the number that contained exactly 2 digits, and the number that contained exactly 3. Even counting the number that contained exactly 1 digit needs techniques that we haven't learned yet. All right, so now the sum rule. The sum rule is nice and easy. Unfortunately, it's restricted. Because it assumes something about the sets, and it assumes that if A and B are disjoint, then the size of A union B is equal to the size of A plus the size of B. Okay? Disjoint. What does that mean? Disjoint means the intersection of A and B is empty. There's nothing that's in A and also in B. In terms of these Venn diagrams, A and B live inside of some universe. But they live completely separately. There's nothing, no element that is both in A and in B. Okay. And I think it's clear why the sum rule is true. If I want to count what's in the union of A and B, well, I just count everything in A, and I count everything in B, and that gives me the size of the union. Because I didn't count anything twice, I counted everything that I'm interested in exactly once. If it was in A, I counted it when I was counting the size of A, and if it was in B, I counted it when I was counting the size of B, and there's nothing that's both in A and B. Okay? Good. So that's the sum rule. Here's a example. Same thing. let's say that a valid, so this is a more sophisticated password system. Valid password is any string of length 6, 7, or 8 over the alphabet sigma, same alphabet as before, that contains at least one digit. Okay, so it's almost the same setup as before, except that the system is a little bit less restrictive than the last one. It doesn't force you to pick a password that has length exactly 8. You can pick one that's of size 6, one that's of size 7, or one that's of size 8. Okay. And now this actually really is getting closer and closer to this kind of annoying password systems that we all have to deal with all the time, right? There's a lower bound on the length of your password. Usually there's an upper bound. They may not tell you it, but try entering a 500 character password and you'll see often that systems won't let you choose that as a password. And there's some restriction on, yeah, it has to be over some alphabet, and it can't use, it has to use at least one of these special characters. All right, so question is, how many passwords are there in this system? How many different passwords are there? And for that we can use the sum rule, and the idea is, well, we want to break this up into into disjoint sets and count each set separately, right? So we have some union, we want to break it up into to disjoint sets and count them separately. So let's say for each n in 6, 7, 8, let Sn be the set of valid passwords of length n, and we saw already S8, that's the set we were just talking about in the previous example, set of valid passwords whose length is exactly 8. The size of that thing is 36 to the 8 minus 26 to the 8. And I think it's not a stretch for us to see then that if we instead looked at passwords of length 7, that the number is going to be 36 to the 7 minus 26 to the 7. And if we look at passwords of length 6, that number is going to be 36 to the 6 minus 26 to the 6. Exactly the same argument, but replace 8 with 7 or replace 8 with 6 everywhere we were doing this. And now let's say S, that's the set of all the passwords we're interested in of length 6, 7, or 8. That's the union of these three things. S6, union S7, union S8. If I look at the Venn diagram picture, I have this universe of pass of all, let's say, strings. Inside of there, I have S6, I have S7, and I have S8. together, these three things make up the set of all the allowable passwords in this particular system. And I think it's clear that these sets are pairwise disjoint. Why? Because every string in S6 is a string of length 6. Every string in S7 is a string of length 7. So there's no string that has length 6, simultaneously has length 6 and length 7. So there's nothing in common between S6 and S7, same thing between S7 and S8, and the same thing between S8 and S6. So they're pairwise disjoint, so we can use the sum rule. And this shows the sum rule for 2 sets, but when you have 3 sets or even k sets that are all pairwise disjoint, it generalizes in the obvious way. So the size of S is just the size of S6 plus the size of S7 plus the size of S8. And we can write that all down. 36 to the 6 minus 26 to the 6 plus 36 to the 7 minus 26 to the 7 plus 36 to the 8 minus 26 to the 8. And that is equal to 2 is equal to this number. So the actual value of this number doesn't matter, really. It's not critical, except that it does teach us a little bit of a lesson. This number here is actually pretty close to the last one. In fact, it agrees on the first 2 digits. So the number of passwords of length 8 and the number of passwords of length 6, 7, or 8, they're not that far apart. So you might have thought that, since now we have 3 different sets, maybe we get 3 times as many passwords, or nearly 3 times as many passwords. You would be wrong, because that doesn't happen at all. And the reason it doesn't happen is because the number of passwords of length 7 is actually much less than the number of passwords of length 8. And the number of passwords of length 6 is even much less than that. So basically, there's something like 26 times more passwords of length 8 than there are of length 7. Okay. All right. So this system has more passwords than the last one, but not a ton more. It's not really much more secure. Okay. Question? Okay, good. So again, something fairly easy, but I hope you see the relevance of this already to computer science, in particular to computer security. Anytime you devise a security system or some kind of authentication system that requires some sort of secret, like a password or something, you better do these kinds of rough calculations to at least figure out that there's a lot of different possible passwords. And sometimes this is non-trivial, in particular when you get into fancier methods, things like biometric security, where things are not so obviously discrete. Like, how many different fingerprints are there? Well, that kind of depends on exactly how much detail you're taking when you take someone's fingerprint. because, well, I mean, you can, if you're sloppy about it, you can end up in a situation where you have many groups of people who have the same fingerprint. Okay. So that is the sum rule. It's very useful when it's applicable. And the thing to remember is you need A and B to be disjoint. And let me just say for completeness, if you have many sets, because we already had to use it for 3 sets, if A1, A2, up to AN are pairwise disjoint, then the size of A1 union A2 and so on up to AN is just the sum of the sizes. We used it already for n equals 3 and saw that the picture is just this box which is with a bunch of different disjoint sets in it. Okay. But again, the utility of this is limited by this assumption that the sets are disjoint, so that there's no element that's in 2 or more of the sets. If you don't have that, then things get more complicated. And that's when you get to what's called the principle of inclusion-exclusion. And here's the basic version. For any 2 sets, A and B, the size of A union B, you take the size of A, you add the size of B. So far it looks just like the sum rule, but you have to subtract the size of A intersected with B. Let's look at a picture to understand why that happens. In general, if A and B are not disjoint, then their Venn diagram looks like this. You have stuff that's in A, but not in B. You have stuff that's in B, but not in A. And then you have stuff that's in A intersect B. And if I want to count the size of A union B, well, if I count everything in A, then I count this region once, and I count this region once. So that's everything in A. If I count everything in B, I count everything in this region once, but I also count everything in this region again. So size of A plus the size of B overcounts the size of A union B, because the stuff in the intersection here is counted twice. How do we correct that? We have to subtract we have to subtract it once. So once we do this subtraction, then the stuff in here is counted only once. Okay. Is that clear? So it's more general than the sum rule because it lets us consider any 2 sets A and B, but it's more work than the sum rule because instead of only having to figure out the sizes of 2 sets, there's a third related set, the intersection set, that we also need to know the size of. So let's look at an example. And we'll look at the set of bit strings, so binary strings, of a length 17 that start with 0, 1, 0 or end with 1, 1. Okay. So, for example, here's one of those bit strings, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. Whatever I do here, just make sure that this is 14 characters long. As long as it starts, it's a 0, 1, 0 followed by those 14 characters, then that's in this set, because it starts with 0, 1, 0 and it has length 17. Here's another one that's in there. I start with whatever I want. I do that for 15 characters, and then I finish with 1, 1. That's another string that's in this set because it's 17 characters long and it ends with 1, 1. So we'd like to know how many of those there are. And we want to use, well, since we're talking about the principle of inclusion-exclusion, that's what we'll use. So A will be the length 17 bit strings that start with 0, 1, 0. B will be the length 17 bit strings that end with 1, 1. And so what I'm interested in knowing is the size of A union B. So let's write down what we need here. The size of A union B, according to the principle of inclusion-exclusion, is the size of A plus the size of B minus the size of the intersection of A and B. So we need to figure out these three things in order to know the size of A union B. And we really need the full principle of inclusion-exclusion. The sum rule doesn't work because there are strings, like this one, that start with 0, 1, 0. So this string is in A. It ends with 1, 1. So it's in B. So that means if we just did the size of A plus the size of B, we would count this string twice. So we really need to make up for that. All right. So let's look at the size of A. The strings in A, what do they look like? They start with 0, 1, 0. And then there are 14 more characters, right? If the string has length 14 or length 17 and it starts with 0, 1, 0, then after the 0, 1, 0 there are 14 more bits. Okay. And it doesn't matter what values those bits have, I'll get a string that's in A because it starts with 0, 1, 0. So how big is the size of A? Yeah, good. So a few of you answered 2 to the power 14. And indeed, that's just because to generate a string in A, I write down 0, 1, 0, and then I write down any string, any binary string of length 14. The number of ways of doing the first step is 1. There's only one way to write down 0, 1, 0. The number of ways of doing the second step is the number of strings, binary strings of length 14, and we already figured out that the number of binary strings of length n is 2 to the n. So the size of A is 2 to the 14. Okay. Now we can look at the size of B. What does something from B look like? B looks like some number of characters. In fact, that number is 15. And then it finishes with 2 1s. So a procedure for writing down something from B is to write down any binary string of length 15 and then write down the 2 1s. The number of ways of doing the first step, writing down a binary string of length 15, is 2 to the 15. And the number of ways of doing the second step is only 1. So the size of B is 2 to the 15. And what about A intersect B? Okay. A intersect B, those are the strings that start with 0, 1, 0. Then there are 12 characters whose value I do not care about. And then there's 2 1s. Okay. Because they're in A, they have to start with 0, 1, 0. Because they're in B, they have to finish with 1, 1. And as long as those two conditions are satisfied, it doesn't matter what goes in these 12 positions in the middle. So again, it's a trivial application of the product rule with the procedure being write down 0, 1, 0. There's one way to do that. Write down a 12-character binary string. There's 2 to the 12 ways to do that. And then write down 1, 1. There's only one way to do that. So we get 2 to the 12. And we're done. So the size of A union B is 2 to the 14 plus 2 to the 15 minus 2 to the 12. Okay. And that is if I calculated that correctly, it's about 45,000. All right. So any question there? All right. Well, we did the sum rule, and it told us how to compute the size of A union B if A and B are disjoint. And it also told us how to compute the size of A1 union A2, union A3, union all the way up to AN if A1 through AN are pairwise disjoint. So I guess the obvious question is, well, what's the principle of inclusion-exclusion when we have more than two sets? And I won't give you the full answer, but I will show you what it looks like for three sets. And it will give you an idea of why, when you have many sets, things become complicated. So here it is for three sets. For any three sets, A, B, C, the size of A union B union C is equal to, you start with the obvious thing. You have to count everything that's in A, everything that's in B, everything that's in C. You have to take away the pairwise intersection. Okay, take away the pairwise intersections. You're still not done. You have to add back the three-way intersection. Okay. Why is that? Well, we can do that with a Venn diagram. We have A, we have B, and we have C. And so let's start counting. When I add up the size of A, that counts everything in each of these regions once. When I take the size of B, that counts everything in each of these regions once. When I take the size of C, that counts everything in each of these regions once. And so I've definitely way over counted. Sometimes I've double counted, and in this particular case here I've triple counted. So that's the formula up to this point. But now we subtract A intersect B. So when I subtract A intersect B, that takes away one thing from there and one thing from there. When I subtract B intersect C, that takes away one from there, one from there. And when I subtract A intersect C, that takes one from there and one from there. That looks much better. It's almost perfect, except that I have not counted the stuff that's in the common intersection of A, B, and C. I had triple counted it before, but now I've subtracted it 3 times. And so I have to add that back in once more, and that's when I get back to this perfect picture that counts everything in each region exactly once. So question is, would I rather you leave exponents, the answer in exponents on assignments, or write down the full final answer? It's up to you. I don't want you to, let's say that I don't want you to skip writing down the exponents and just jump straight to this. So definitely write down this part, and if you like, write down this thing as well. I like to do it sometimes when I'm teaching because it gives people a sort of a feel for the numbers. Like here, if you know a bit about powers of 2, 2 to the 16 is about 65,000. And so here, these are, the number of these things is less than the number of binary strings of length of length 16, but more than the number of binary strings of length 15, which is only about 32,000. So it just gives you a feel for these things. But it's really up to you. And really, this is the trivial part, right? This is the part you can do with a calculator. I like to use Python as a calculator because in this course we will sometimes get enormous numbers. Python has no problems with those. All right. So that's the principle of inclusion, exclusion for 3 sets. And what happens when you have many sets, n sets? Well, then you get a huge formula here. In fact, if I look at this formula, how many terms does it have? It has 1, 2, 3, 4, 5, 6, 7 terms. And the formula for 2 sets had 3 terms. Anybody want to guess how many terms are in the formula for 4 sets? So the sequence is looking like 3, 7, yeah. The answer is 15. Okay. And for 5 sets, you would have a formula with 31 terms. Why is that happening? So these are all 1 less than a power of 2, right? There's 1 less than 4, 1 less than 8, 1 less than 16, 1 less than 32. Why is that happening? It's happening because the terms that you get are, you need 1 term for each subset of, in this case, A, B, and C. More specifically, you need a term for each non-empty subset of A, B, and C, right? Here's the term for A, here's the term for B, here's the term for C, here's the term for AB, here's the term for BC, here's the term for AC, and here's the term for ABC. So going right back to the first thing we did in this class, the number of subsets of these things, so meaning the subsets of the set ABC is 8, and I need to consider all of them except for the empty one. So the number of those is 7. And in general, that's what happens. If you have n sets and you want to use the principle of inclusion-exclusion to compute their size of their union exactly, then you get 2 to the n minus 1 terms. So not terribly practical, at least if you're using it by hand for anything really larger than 3 or 4. So let's very quickly do an example of 3, and we can do it quickly because it's going to be close to this. It's bit strings of length 17. They start with 0, 1, 0, or they end with 1, 1, or they have 1, 0 at positions 7 and 8. Okay. So they either start with this, or they end with this, or at some particular place in the middle they have a 1, 0. Okay. So that gives us a set A, the ones that start with 0, 1, 0. Gives us a set B, the ones that end with 1, 1, and then there's a set C. C are the ones that have a 1, 0 at positions 7 and 8. So what do those look like? An element of C looks like this. I don't know, I guess there's 6 things here, then there's a 1, 0, and then there's 9 things here. Right, that's a total of 15 spaces to fill in, right, because if they're in C, there's 2 spaces in the middle there have that 1, 0. And again, you can use the product rule here. The rule is write down these 6 things. There's 2 to the 6 ways to do that. Write down 1, 0. There's 1 way to do that. And then write down these 9 things. There's 2 to the 9 ways to do that. So the number of ways is 2 to the 6 times 1 times 2 to the 9 is 2 to the 15. So size of C is also 2 to the 15. Now we want to use this formula. We need to figure out all of these things. Size of A intersect B, that we already calculated was 2 to the 12. The size of B intersect C, we haven't done that one yet, but we know what these things look like. If you're in B and C, then you have 1, 2, 3, 4, 5, 6 of whatever you want. Then you have 1, 0. Then you have 7 things. And then you have 1, 1. So this is what, if you're in B intersect C, it's what you look like. So the total number of things to fill in here is 13. So that's 2 to the 13. And we also need to know the size of A intersect C. Those are the ones that have 0, 1, 0, then 3 blanks, then 1, 0, and then 9 blanks that we get to choose. There are 3 plus 9 bits to fill in here. That's 12 bits. So there's 2 to the 12 of those. And then finally, we need the size of A intersect B intersect C. And those look like 0, 1, 0, 3 bits whose values don't matter, 1, 0, 1, 2, 3, 4, 5, 6, 7, and then 1, 1. Okay, so 3 here, 7 there. So that's a total of 10 bits that we get to choose. So that's 2 to the 10. And now we can write down the answer, which is size of A union B union C is 2 to the 14 plus 2 to the 15 plus 2 to the 15 minus 2 to the 12 minus 2 to the 13 minus 2 to the 12, and then finally plus 2 to the 10. And that is 66,560. Okay. All right. And so again, just to compare this to something, this is kind of close to, it's a little bit more than the number of binary strings of length 16, which is 66,000 or 65,566, I think. The number of binary bit strings of length 17 that satisfy at least one of these 3 conditions is approximately the same, or I mean it's comparable to just the number of bit strings of length 16 with no special conditions. All right, so that is a good place to to end for today. I will answer questions for the next 5 minutes or until until nobody has any. Are we ever going to have to use the principle of inclusion-exclusion on 4 sets or higher? That depends on your definition of ever, and it depends on what you plan to do with the rest of your life after you take this course. In this course, there will not be a question that requires you to use the principle of inclusion-exclusion on 4 sets or more. It just won't happen. Maybe at some point later in life you'll need to use it. I don't know, but you can look it up and you know it exists. Are we going over Ramsey's theorem in more detail, or can we solve question 1 now? You can solve question 1 now. The proof of Ramsey's theorem that I gave on the first class was complete. Question 1 follows the same lines as that proof. If you would want a hint on how to begin that, so it asks you to do an inductive proof. On the first class we did the value k equals 2. The value k equals 1 is trivial, and it's the first part of the question. So it would be instructive for you to just redo what we did in the first class, but see where because it's for k equals 2, at what point you're using the inductive hypothesis, k equals 1. Where in that proof are you using the inductive hypothesis? And then you'll realize, oh, it's exactly the same place I have to use it for general values of k. How do we determine the sign for over 4 sets? The signs alternate. So you always start by adding up the sizes of the 4 sets, and then you have to subtract off the sizes of the 4 individual sets. Then you have to subtract off the sizes of the pairwise intersections. That gets everything looking good in the regions that are only contained in 2 sets, but the regions that are contained in 3 or more sets, now you've subtracted too much, so you add back in the triple 3-wise intersections and then subtract the 4-wise intersection. So the signs alternate. What does pairwise disjoint mean? Pairwise disjoint just means you say it when you're talking about more than 2 sets. But it just means that if I look at 2 sets, if I have A, B, and C, these are pairwise disjoint because A intersect B is empty, B intersect C is empty, and C intersect A is empty. Every pair of sets is disjoint. I don't understand why in the previous examples 36 to the 8 minus 26 to the 8. I thought that it could be 36 to the 7 times 10, any choice of digits till 7, and then multiply by 10 so that at least one of them is a digit. Well, okay, so you have a proposed formula which is 36 to the power 7 times 10, but that would only count passwords that look like this, right? Letter, 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 1, 2, 3, 4, 5, 6, 7, and then a digit, maybe 0, right? So the number of things that look like this is 36 to the 7, or not 36 to the 7, 26 to the 7, I see. So let me do this right. So here you have letter or digit, letter or digit, letter or digit 7 times, and then the last thing is a digit. But the question doesn't say that the last character has to be a digit. The question says that at least one of the characters has to be a digit. And in particular, if you use the digit in the first 7 characters, the last one can be a letter. I won't answer questions about 2402 during 2804. Okay. Yes, password matters. So when we talk about string, or for passwords, order matters, or when we talk about strings, we really mean a sequence of characters. And when we say a sequence, we're really talking about characters occurring in some specific order. I don't know of any password systems that have a bag of characters that you throw in and it tells you if that's the right bag or not. It doesn't work because you need order. Yeah, I mean, it already assumes order. If you say 36 to the 7, you've already assumed order because 36 to the 7 counts the number of sequences of length 7 over 36 symbols. So if you didn't assume order, then there's something else. Then that answer doesn't make sense for a different reason. What part of the solution passes the condition that at least one digit is in the password? What it looks at is the set of all strings, and it takes away the ones that don't have any digits in the password. So if I take away all the strings that have no digits, then I'm left with strings that have 1 or more digits. Why did I add the 2 to the 10 and not subtract? Because the principle of inclusion-exclusion, though it's marked off here, says that that last term we should add. And why was that? Well, when we did this carefully, we saw that after you get past the first 6 terms, you haven't counted the stuff that's in A intersect B intersect C anymore. You had triple counted it, then you subtracted it 3 times. You need to add it back in. How does the principle of inclusion-exclusion apply to binomial coefficients? It doesn't really. We will prove that the number of subsets, k-element subsets of a set of size n is n choose k, and nowhere in that proof will we use the principle of inclusion-exclusion. If in the assignment it asks for the principle of inclusion-exclusion, it's not about for proving anything about the binomial coefficients. It's for solving something in the assignment where you have 2 or 3 sets that are whose union you need to know the size of. All right, so thanks for tuning in. See you next class.